Okay, so in this video, I'm going to talk a little bit about kinetic energy, which is the third type of energy that we're going to be dealing with pretty consistently. And then we're going to go into talking about energy transformations and how we have changes from one type of energy to another. So the kinetic energy formula is very, very simple. I'm not even going to do an example with it because you'll have a chance to work on it in class. But I do want to point out that right now we are dealing with only translational kinetic energy. And what that means is we're only going to be dealing with an object that is moving um, like in a linear fashion. Later on, we will deal with objects that are also rotating while they move. So, like a ball rolling down a hill. And when it does that, you have the translational kinetic energy that's moving it down the hill. And then you have the rotational kinetic energy, which is actually causing the ball to turn. Okay. And that you have to deal with separately. So, we will deal with that in our second um, rotational motion unit. All right. So right now we're only doing translational kinetic energy. And this is just energy due to an object in motion. Okay. If an object has motion, it has kinetic energy that it can do whatever with. It can use that to transfer to other objects or to move other objects, to use it to just move itself. But the formula for that is K equals 1/2 mv squared. So K is our symbol for kinetic energy. It is a capital K. So make sure you distinguish that from the K in Hooke's law. M, as you can probably guess, is mass, and V is velocity. Okay. So nothing crazy or new there. This is still going to be measured in joules. So just like any other kind of energy, nothing crazy there. You just put a capital J after your answer. All right. Now, when we're talking about energy transformations, we need to kind of talk about two different things. Number one, you have learned that energy is neither created nor destroyed. That's the law of conservation of energy. All right. Um, but in the absence of what we call non conservative forces, which are forces that cause us to lose energy outside of what our system currently is, mechanical energy is also conserved. Okay. So when we say total energy is conserved, we're talking about on the scale of like the universe. If a car slows down and some of that energy is lost due to friction, it's not that that energy is disappearing, it's just that it's being dissipated in the form of heat to the atmosphere. Okay, so we're considering kind of a universal scale when we say energy is not created or destroyed. For our purposes, our system is going to be on a much smaller scale, where it might just be the car and the earth and the road that's in our system. So we might say we lose energy. But if we don't think, or if we don't consider our forces that cause a dissipation of that energy, like friction or air resistance, then mechanical energy is going to be conserved. Mechanical energy is the sum of the gravitational, or I'm sorry, of the potential and the kinetic energies. So mechanical energy is the sum of the kinetic and the potential energies. All right. And so what you need to realize is that energy of an object is very fluid and it can change easily from one type to another. So as a skier goes down a slope, what started as just potential energy, as it goes down the slope, some of that potential turns to kinetic, and then eventually towards the bottom, all of the skier's energy will be kinetic. Okay. And then in a world without friction, she just keeps going forever, right? So that kinetic energy just remains. Um, so you could also have, the opposite situation. You could have, um, something, a box being slid up a ramp. So it's given an initial force. So it has kinetic energy initially. As it goes up the ramp, it's going to slow down and it'll gain potential energy. All right. You could have a spring that's stretched out. So all of its energy is elastic potential. And then you let go of the spring and it transfers that, and it flexes back and hits an object or releases an object. And so then that becomes kinetic. So you can have really easy, simple changes from one type to another. Now, as we know in the real world, there is never a perfect conservation of energy unless we're talking about on a universe scale. So, as I mentioned, if our system is just like one object in the earth, you can have a dissipation of energy. That does not mean that energy is getting destroyed, it's just transferring to a form that is no longer mechanical. So, that could be like thermal energy, which is heat and is the most common form of dissipated energy. All right. So what we're gonna do here is kind of um, derive a nice, fun equation to work with based on the principle that energy is conserved, and we're gonna work under the conservation of mechanical energy first, and then later on we'll factor in friction. Um, so we're going to use the principle that the initial energy is equal to the final energy to set up an equation here. So let me go back and get a slide so we can do this. All right, so new slide. That's what we want. All right, so we're going to use this little mini equation I have down here, which just says initial energy is equal to final energy. All right. And so what we can do is we can say, well, we know that mechanical energy is the sum of the potential and the kinetic energy. So we could say potential energy, which could be US plus UG. So it's the sum of the potential and the kinetic plus the kinetic energy that it has to begin with. And I'm going to put little zeros next to each of these just to show that those are all initial. Well, that energy has to be equal to that object's final sum of potential and kinetic energies. So US plus UG plus K. All right. And so then, based on whatever you're dealing with, you could use whatever parts of that energy you needed. So let's say we were going to do the case of my little skier friend here. So here's her skis. And okay, so she starts at the top of the hill. Well, at the top of the hill, if she starts from rest, the only kind of energy she's going to have is gravitational. Then at the bottom of the hill, I don't know why her head got suddenly very large. At the bottom of the hill, the only kind of energy she's going to have is kinetic. There's obviously no elastic involved. If she starts from rest, there's no initial kinetic. And if she's at the bottom of the hill, there's no final gravitational. And so then we can plug in our formulas for this and then have a formula to work with. So my formula for gravitational potential energy is mg delta y. And that's, we can set that equal because the total amount of energy at the beginning has to equal the total amount at the end, equals 1/2 mv squared. All right. So if we know the height from she started from, we can actually find her velocity at the end because my mass here will just cancel. I plug in 9.81, I plug in her height, and then I can solve for v and figure out what speed she's going to be going at the bottom of the hill. Okay. And so you can use that initial energy equals that final energy relationship to solve a lot of problems if you just remember to plug in your energy equations. So we're going to work with that a lot in class. It'll probably take us several days, and then we'll move on to work.